So it's I hope there's no misunderstanding about it. It's not really an exercise session. It's more, well, it's a proof which is a little bit more technical and maybe it was not appropriate for the talk. Anyway, so I will try to breathe a little bit, so to go slower. So if you start with the Laurent series, okay, and you take a rational function such that r of 0 is equal to 0, then it makes sense to compose the Laurent series with the rational function r. That's it. Okay. And one can find something like that. I'm going to write it as a lemma. It's actually more a remark than a lemma. If psi, I don't want to say where psi lives for now, is a solution of the functional equation psi r of t equal r prime of t psi of t, then the endomorphism phi commutes, then one can define a derivative psi d over dt. So multiplication is a derivative such that delta composed with phi is equal to phi composed with delta. Okay, so it's more a remark than a lemma. Anyway, the verification, it's quite straightforward. It could be an exercise for younger student. Then, yeah, let's start this way. Delta of phi of f, it's equal to psi d over dt of f over t on that one. And this is psi r prime of t f prime over t. Well, and that's it. The functional equation gives you phi which is exactly, okay, so this is a small remark, and well, the difficult thing is to find the psi. Luckily, our elders have thought about it. So this psi is important. It's studying rational dynamics, and in Ecal calls it IT. I wouldn't know how to translate it. Iterative logarithm. I think it's a fair translation of this. So in his work, so it's something that it's actually studied by people in dynamics, and one can construct the psi using some classical works. It's so there are two. Well, for all over the talk, I'm working under this hypothesis, which is not really essential, but I will comment on it. So r of 0 is equal to 0. R prime of 0 is equal to 0 or 1. And actually, this includes the cases where it's also you take a roots of unity. Since one can replace phi by power of phi. So whenever the first coefficient is a root of unity, you can just replace phi by an iteration and suppose that it's 1. So this is an hidden hypothesis. And I also suppose that R composed with itself, it's always different from the identity for n times for any n. Okay, so this is going to be for the whole talks. And so that's something which is called Abel equation. And that in the case where R prime of 0 is equal to 1, one can find a power series, tau, which belongs to t plus t squared. Okay, so it starts with t and satisfy the functional equation so to find it, you just plug in a form of power series, and you solve the coefficient recursively. It's not very interesting actually, but it exists, and it doesn't converge. And if you derive this functional equation, you get almost this one here, of course. Okay, and actually you can just take psi to be 1 over 2 prime, and so 2 prime starts with a 1, so everything is nice and sound. Okay. So there's an old theorem which has which focus on something similar by Reed and 1926, and then it has, I mean, the result as stated is the combination of Reed theorem and another theorem, which is by Baker and Berg-Weiler, and that's 1995. Okay, so under this assumption here, psi is always the transcendental over COT. So these things that you find here is never a solution of an algebraic differential equation. So Reed theorem is a tough theorem, and this is a 4 pages long paper, but it's, I mean, it takes much, I mean, it takes a lot of time to read for a 4 page. I mean, it's really dense. Anyway, it's an important, I mean, it's difficult. And Joris mentioned a proof of the older theorem, which is and this Reed theorem uses the same strategy than the proof he mentioned, and stop. So, in it's too high. The other situation is the one considered by Botcher equation. It's in the case where r prime of 0 is equal to 0, and we call D the order at t equals 0 of r. Then one consider another kind of functional equation, but the solution has the same shape. I call it the same way because otherwise. So there is this tau in t plus t squared c of t, such that tau of r of t it's equal to tau of t to the power d. Okay, so those are functional equations that actually are used to linearize the function r next to 0. So this rational function next to 0 is x to the power d. If you consider the change of variable, this functional equation are used to change the variable so that your rational function in the small neighbors act as a monomial. That's why people in rational dynamics.
What about the leading coefficient of R?
It doesn't matter.
Was it supposed to be 0 or not?
The leading coefficient?
The leading or the constant coefficient? No, the R of 0 is 0, right?
Yes.
And then R prime of 0. So the leading coefficient doesn't matter. Okay.
So it's tau.
Yes, maybe you need some. Yes, maybe you need something here. Yes, anyway, there's a.
On the blackboard above here, is it like everywhere is it a tau? Because you have tau of R of t equals tau of t plus 1?
When r prime of 0 is equal to 1?
Yeah, but is it always the case that R of 0 equal to 0? Because then if you compose.
So because if it's RT plus 1 or tau t plus 1? Because if you replace by 0, we're going to find tau of 0 is equal to tau of 0 plus 1, which is weird, right?
Yes.
Yes, I understand.
So it's RT.
Yes, yes, the parenthesis. Let me.
It's tau t plus 1 in the bracket.
Let me think about it. I can't remember. That's not. I have the paper. That's not. Oh, we haven't redone the calculation. Sorry. Well, I think it's the way something like that. Well,
usually you
and
iterate a function, right?
yes, anyway.
So it's written. Usually it's written differently, I think.
Yes.
You say something like.
I'm going to say something which is.
Tau of t plus 1, which should be equal to r of tau of t, something like this.
Mm-hmm.
That is basically what one does.
Let me say something which I think it's right. Okay.
Yeah.
And
If you take the inverse operation, you get. But
yes, the inverse. If it's
you're considering the inverse of the Abel equation.
yes.
So
The Abel equation is R of M of S equal to M of S plus 1. Or anyway.
well, you conjugate with the shift, right? So
In any case, something is quite sure, is that this one you can find a solution which is a power series directly, because I have the calculation under my nose. It's almost the only case you can do it. Okay, this I'm pretty sure it works. Okay, and in this other case, it's way more complicated, and it's actually a theorem by Botter. You have to take a limit of analytic function. Is a little bit more complicated to actually calculate it. I lost my paper. And well, and to solve this, you need something more. You need a logarithm, meaning that if you call log tau the primitive of tau prime over tau, then log tau belongs to C of t log t. And so psi looks something like this, tau over tau prime log t. So and if you want to check it, well, from here you get something like tau prime over tau of rt times r prime t equal to d tau prime over tau, and log of tau of rt, it's equal to log of tau of d. Okay, so if you check, well, altogether you get the psi r of t. From here you're going to get an r prime over d times tau over tau prime times d log tau.
usually this one you just reduce to the shift case by taking constant logarithm.
Yes. Anyway, that's not the... And what happens here is that always for a theorem by Ritz and the other two guys, so so either a function m, which is the inverse of tau for the composition, is rational, or psi is the transcendental. Okay, so in any case, the situation is pretty similar. And there's a third case that, which was the original one considered by Reed, which we didn't consider, is the case where, remark, R prime of 0 is equal to Q, which is a complex number, and we are not in the situation above. So Q different from 0, 1, roots of 1. Well, in this case, you get a psi which is either rational or the algebraic or the transcendental. So this case, well, we know how to do it. This case is all right too. You will see in a moment. And we didn't know how, I guess it's not too complicated, but we didn't know how to do this case here. It's surely more complicated than the others, and we didn't have any examples, any application for this situation. So we were not very motivated to go through the missing case. Maybe one day. So, so this case is totally classified by Reed. You even know the equation, you know everything, but still it sounds a little bit more. It's not because you know everything that you can do everything, usually. So anyway, the theorem is the following. So poor Marnie. Okay, so under the hypothesis which I wrote up there, let Z be a Laurent series, be a rational function such that Z of R of t equals Z of t plus B of t. Then either Z is a rational function or is the transcendent. Okay, that's the statement, which is pretty much as the other statement we saw yesterday. So first of all, let's, where is it? First remark. Using the theorem up there, when M is rational, then R of M of S is equal to M of S to the power D. So maybe you can guess it. This functional equation actually reduced to a Mahler equation. Okay, and well, I just set S equal tau of t, or t equal m of s, as you like it. Never know. So w, take a function w, which is equal to z composed with m, and a rational function b beta, which is b composed with m. Then here, z of r of t, you put lots of m composed with m minus 1 in the middle. This gives you this times okay. Yes. And this is w of s of d. Okay, so you make a change of variable here, and this is going to be w of s, and this is going to be beta of s, just rewriting this one. And this is a Malor equation, which is well studied. And actually, in this case, this result here is well known, and there are several proofs in the literature. There's the one by Nishioka, 84. Then there's a proof by Randé, 92. And then there's a Galoisian proof by Nguyen in 2011. So it's a known fact. And so in this situation, we know that W is either in C of t or D transcendental. But W, it's Z composed with a rational function, doesn't change the nature of Z, so you can deduce the same from Z. So actually the things to do is one psi is the transcendental, which covers all the other cases. That's one thing. So we can suppose that C is the transcendental, and I have yes, I like to do a small remark here. It's really not easy to establish whether you are in the situation where this function is rational or psi is the transcendental. And well, we did it just for one of the examples I showed yesterday for the trees, where dr is this polynomial, so you can show that you cannot reduce to a Malor equation in this. So we did really by hand, took 3 pages of calculation that showed that it was not possible to reduce this situation to a Malor equation, and people in rational dynamics could do it in 10 lines using theorem by Milne. I mean, anyway. One can prove it, but it's not so easy, and so it's nice that you don't have to check in what situation you are. So okay. And 1, 2, 3. And so to go on, in the case where psi is D transcendental, I just need to do a small digression. Of differential algebra. So imagine you have a field K here, and an extension K tilde here, and L here, and all extension of differential field. So practically, in this, for us, we have that K is the rational function, K tilde is the rational function where we have had psi, psi prime, and so on and so forth. And L, it's L over K is D algebraic. What does it mean? It means that for any f in L, f is solution of an algebraic differential equation. Okay, so this, all the things in here are the algebraic. And all the things in here are differentially, for any f in K tilde minus K, is f is D transcendental. So it's a purely transcendental extension, purely D transcendental extension. So here you have, in this extension here, you just add in solution of a differential equation, algebraic differential equation, and in here you add an element and its derivative, which is differentially transcendental. And of course, you cannot find anything which is differentially transcendental in this extension. If you find something, it would be a rational function in psi and its derivative. So if it if something in this extension satisfies a differential equation, psi itself would satisfy a differential equation because it would be a rational function in psi and its derivative. So this, you cannot find anything in here which is solution of a differential equation. And so there are two small remarks that one uses over and over again. The first is that L, well, that's completely trivial because you cannot have anything in the intersection since these things are solution of differential equation and these things are not. And the other things is slightly more sophisticated. It means that if you find something in capital F, the big field, which is D transcendental over K, then F is D transcendental over L. So if you cannot find any differential equation with coefficient in K, you cannot find any differential equation with coefficient in L. And this is the analog of what happens for algebraic extension. If you have something which is transcendental here, and this extension here is algebraic, you have exactly the same theorem for algebraic extension. But if you want to prove it, just to so let us suppose that we have phi f, which is the algebraic over L. So f satisfies a differential equation with a coefficient in L. Then we can suppose that L is generated by the coefficient of the equation and their derivatives. Which means that L is finally generated. And then it's just a matter of transcendental degrees. So the yes, the transcendent degree over L of L, where I add f and all its derivatives, it's smaller or equal to the transcendent degree over k of the same things. So, and this is equal to the transcendent degree of k over k of L plus the transcendent what am I saying? The transcendent degree of L, okay, plus the transcendent degree of k of f prime. So it means that you have something transcendental here and something transcendental in this extension, and you put a transcendent base together, and this is finite by assumption, so these things here must be finite, okay? So you just add the finite base of transcendence at each time, and well, it's another way of saying that if your function satisfies a functional equation over L, and that every coefficient of the functional equation satisfies itself a functional equation, you can descend your functional equation, maybe getting a higher degree, okay? So it's quite the same of, analogous theorem on algebraic extension, field, where am I? And before really getting to the proof, I would like to recall the statement from yesterday, which was the following. Theorem, corollary, I don't know anymore, let's say theorem, which, well, the first time it appeared like that in Ardoin Singer, 08, and then it has been rephrased in many places to adapt to many situations. So you have a field and K, F over a field K, like here, and F comes with an endomorphism, and a derivation, and delta around composed with phi is equal to L, and K is stable by phi and delta, so they act on K, and C, let's say C is the field of constant of invariant invariance of F. So basically F, it's the Laurent series in what follows. And suppose that you have Z in capital F and B in K, such that phi of Z is equal to Z plus B. Then, the following are equivalent. Z is differentially algebraic over K. 2, there exist n greater or equal to 0. There exists lambda I in C from E to 0 to n, not all 0, and such that so G sum over E lambda E delta E of Z, how did I call the derivation delta, belongs to K. And a third condition is that there exists n greater than 0, or exists lambda I as above, and there exists G in K such that phi of G minus G is equal to lambda I, the derivative, the i's derivative of the coefficient of the equation. So all these three characterizations are the same, are equivalent.
It's the EF product. It's a product, or it's the EF derivation of B. When you put the power I and Gi, for instance, it's lambda I partial I Z. So it's the EF derivative.
Yes, it's the derivative delta. Partial, I applied eight time. I time. I'm going to get it. Yeah. Okay. And yes, that's the main ingredient of the proof, and we have. So where is it? The theorem is here. So there are a few. Well, the first things I'm going to start here. Well, if B is equal to 0, then Z of RT is equal to Z of T. It's not very interesting. Z belongs to C, and the theorem is true. Otherwise, so we can suppose B different from 0. And okay, and I am going to restate the notation. So compared to this small diagram there, K is the rational function, K tilde is the rational function where we have had psi, which is which you need to be able to use your derivation. Okay, psi, and then we suppose by contradiction, and then we go on with the proof, we suppose that Z is the algebraic, and then we consider the field L generate over K by Z and its derivative Z prime, and so on and so forth. So that this extension is the algebraic. Whatever you find this extension is the algebraic over K. Okay, and well, I still need to say what's F. Well, F is C of T, and you may be obliged to add the logarithm, or maybe not. Okay, but it's the huge field where you can do whatever you want. So, once you have It actually takes more time to introduce things than make the proof, the actual proof. So the first step, step 1, is that if psi is the transcendental, then z prime is a rational function. Okay, and that's so to prove this, one uses, of course, the theorem there. And so if, and I remind that we have supposed that Z is d-algebraic, and we want to prove that it's rational. So if Z is d-algebraic, there exists n greater than 0, lambda I in C, not all 0, blah, 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 all the things, such that our G is equal to lambda I delta I of Z belongs to K tilde on one side, just because Z, we know that G, by the theorem up there, that G is the base field on one side, but it belongs also to, it's K tilde. Well, I did it. I should have put a K tilde everywhere. The field, in this case, the field which is invariant by the derivation psi d over dt is actually K tilde. And sorry about the inconsistencies. And well, here, what does this things live? Well, it lives in L, which is the rational function where I have added all the derivatives of psi, of z, and then you have to add all the derivative of psi until a certain level. But if you do it a little bit more with paying attention, you only need to go to the step n-2, and then I should have written in the middle. You have a lambda n. Let's do it. G belongs to K tilde intersection with lambda n, psi to the power n-1, the nth n-1th derivatives of psi plus L of psi until psi to the n-2. Now, why is that? You have that the derivative of z is just psi z prime, and if you iterate twice, well, that is psi times psi z prime prime, so it's psi prime z prime plus psi square z second, and you keep going, and you will see that you always, if you iterate the derivatives, you get this term at the beginning. You always have a power of xi. Okay, so this is the fact that G starts with this term is just proved by recurrence. And well, the point is that the fact that psi is the transcendental means that all these things are algebraically independent. You can look at this as polynomials and this thing as variables, as transcendental things, and you can derive with respect to them. So you can apply to G just n minus 1 n minus 1 and d over d psi n minus 1. Just because they are transcendental, then this is a ring of polynomials in the derivative of psi, and this is a ring of rational function in the derivative of psi. So you forget that it's a function and you just derive with respect to it. And you apply this to G. And because of this expression here, what you get, it's lambda n. I forgot the z prime, sorry. Z prime, which is here. Lambda n z prime. And those derivatives, they live invariant k and there's things here. So this belongs to k tilde, okay? Because, I mean, k tilde is just a field of rational function in those things. So, but k tilde over k is purely d transcendental. So you cannot find anything which is d algebraic, and this is d algebraic. So the only possibility, which is the meaning of this remark here, so we have an extension of the rational functions where there is nothing which is a solution of a differential equation. We have something which is solution of a differential equation. Well, the only possibility is that z belongs to k, which is the rational function. Okay, z prime. So it's not done yet. So we haven't proved that if z is d algebraic, then it's rational. But we are halfway into the proof. We have proved that the derivative is rational. In a way, we just need to prove that z prime cannot have any residues to conclude that z is rational, okay? If it doesn't have residues, you just can integrate. This is page 3. And so the second step is that z prime belonging to c of t implies that z belongs to c of t, of course, under this assumption. So let us isolate the part of z prime which has non-zero residues, something like that. Okay, and then there's a rational part which I call omega prime for some omega in c of t, because we can find a primitive of this part. So just to remember that we can find a primitive. And well, what happened? It happens that so ci and ai are complex numbers, of course. And so there are, first of all, we know that phi of z is equal to z plus b, which we say that phi of z prime, r prime, is equal to z prime plus b prime. Just is the derivative of the composed function. And so we have 0 equal to phi of z prime, r prime minus z prime minus b prime. And now we plug in these things here, and we obtain that we have ci times r prime of t over r of t plus minus a of t minus ci times t of a of I sines plus phi omega prime r prime omega prime minus b prime. And this part here can be integrated, I mean, admits a primitive in the rational function, while this part here is, is the logarithmic derivative. If you set Si equal to t minus ai minus t minus ai, then you just have here that is equal to ci times si prime over si. Okay, so it's the logarithmic derivative of a rational function. And plus these things which has no residues where in any point. Okay? And this is equal to 0, so of course this part must be equal to 0. Every bit of it must be equal to 0, but in particular this part must be equal to 0. And we have supposed that b prime is different from 0. So this implies that omega prime, prime, and with b prime different from 0, because we have supposed that b, where is it? Is non-zero? No, sorry. B prime is different from 0 because z is not a constant, so z prime is different from 0, and so yes, b. What am I saying? Yes, z prime is different from 0. So we have this, and while the primitive, a primitive of omega must verify phi omega equal omega plus b. And since b is different from 0, this primitive must be different from 0, which means that phi of f minus omega, it's equal to f minus omega, and omega is in C of t. So this functional equation says that I have collaborators that likes to call the solution z, and other likes to call it f, and it mix up some in my head. So z and omega, they're different. Their difference is a constant because they are invariant by the operator, and this implies that z is equal to omega. Because they are solution of the same inhomogeneous functional equation. So you have that phi z minus omega is equal to z plus b minus b. And so it just erased because they are a solution of the same inhomogeneous functional equation. So they are invariant by this composition. And so this thing is in C. And so z is a rational function, okay? So that's... Oui, on conclut. And so that was yes, that was everything I wanted to actually say in the yes, and
So what did you just prove? We started with
That is a rational function.
yes, since this equation has a rational function solution, all the other solutions are obtained adding a constant, so z is a constant. So if you suppose that z is the algebraic, it's excellent. Z is rational, so if you suppose that z is the algebraic, then it's rational, which is actually the statement which I cannot find anymore. Oh, it's here, just under my nose. Either is rational or is the transcendental. So if you suppose that it's the algebraic, you conclude that it's rational. Okay. So I stop here, and I just write small things here. Is that if you consider this functional equation here, you get something a little bit more. You get either that Zn is in C of t, or that Z is the transcendental. So you can actually have something algebraic when you have this when you have multiplicative order 1 equation, and the reason is that you just take the logarithmic derivative, so the n comes as a factor. Okay, thank you, and sorry about that.